but we're getting there. Okay, I put the title 3D laser scanning, and yeah, since then Alan says I'm the laser guy, as I said. Actually nowadays we dropped a little bit laser scanning and we talk about reality capture technology, because it's not just about laser scanning. Laser scanning is just one of the technologies, but it's the most prominent one at the moment where everybody talks about this, and many of you are probably using, and the fact that the whole gathering is sponsored by many technology companies who sell this technology means a lot already. I head a lab, so before I get into details, I actually head a lab that we call the Cyber Build Lab. And we actually do a lot of things in this lab, and what I talk about today is just one part of this. One of the things we do at the moment, we have a few projects going on. For example, we're developing immersive, what we call hybrid reality. Actually, a lot of people use augmented reality wrongly, or in a general matter, and that can confuse people. But the idea is to we developed an immersive system with, like Oculus goggles, but the difference is if you raise your hand, you see your actual hand in it, so you really feel totally immersed in it. And that increases the sense of being there, but it actually has other very important applications down the line beyond just at school. Actually enables a lot of things. Another thing we do, using motion sensors to track the bodies of workers in order to infer whether they are at risk of musculoskeletal disorders. This is an ongoing project, and we develop the whole infrastructure. It's all wireless, you can actually wear it on a job site, so there's no like big wires computers. It's closer to reality than just a research project. Another really interesting one I won't have time to talk about, it's an ongoing project with a company in Glasgow. It's called Urban Plan AR. Actually, it's a hybrid reality, it's not augmented reality just. The idea is to let people take their tablets. They know they have a new design in the city. It's meant for urban environment, and by using the tablet, you should be able to see that design in its context. That's great for urban planners, but that's also great to engage with the public. This is what is planned. I was there last week in Gothenburg, and they planned the biggest skyscraper in Sweden, and I think one of the biggest in Europe. And Gothenburg is not really a high-rise city, and they planned this huge structure. And a lot of people are asking questions about it. It's like everybody's worried, but nobody can actually visualize what it is. And obviously the developer gives them great pictures, but they obviously pick what they show to them. They don't want to show the more controversial part. So this is about empowering people, letting people see what things will look like. We hope to have a prototype by the end of the year. Scan-vs-BIM, this is what I'm going to talk about a lot today. Just by curiosity, who has ever seen the acronym Scan-vs-BIM? Wow, we are achieving something. Okay, great, thanks a lot. And then at the end, I'll conclude with a little bit of work on point cloud processing in the heritage area. So that's the one here, and I want to explain. We also do an interesting project. It's quite slow at the moment, but planning for scanning. So if at the end of this presentation you realize there is a lot of potential to use scanning during the construction process, a lot of the work we've seen so far, actually we have running session in this conference on Scan-to-BIM. But actually, if you have a design model and you plan to do scanning, you could actually use this BIM model to kind of plan, where should I put my scanner? And at the moment, this is done a bit of an ad hoc way by experience. The people, the surveyors, they come, they look at the scene, or they may have 2D blueprints before, and they kind of figure out. The idea here is to do it like in 3D. If you do structural scanning, obviously your manual approach might work really well, and actually we've done some work with Sean, and we've seen that expertise, people with just their expertise or experience, they're really good at doing that. But when you start looking at intricate scanning of MEP works, etc., this just becomes too complicated for a single mind. So we try to help solve that problem. So this is a range of things we do. That's the website of CyberBuild. We have a few videos. You're welcome to have a look and give some feedback. So the presentation, a few sections. I'll talk about reality capture quickly, not just about scanning, laser scanning. And then I'll do a bit of a review of Scan-to-BIM, roughly where we are. And I'll try to steer you towards Scan-vs-BIM, which is what we've been working on since about 2004, something like that. That was at the time when our laser scanners fit in a box huge like this. It was like weight ton. It was impossible to carry around. It's horrible, but we did see the potential. And then at the end, heritage survey. So actually these kind of things, it's even almost outdated. They evolve so fast, the laser scanners. But it's just like, it's a great piece of kit because it's very robust. It works in a wide range of environments. It can scan very high accuracy. Actually now it's down to almost sub-millimeter, some certain distances, sub-millimeter accuracy for single point, which is very important. Super dense data. It's almost too much data, it's almost too beautiful. You just don't know. I mean, the problem is you end up having half a gigabyte file, and you still have to deal with these things. But it's not just about laser scanning. Now there is photogrammetry photogrammetry outdates laser scanning as a technology. It's been used for a long, long time. The fact that cameras are now cheap, and also there's some software being developed to make the photogrammetry process much more streamlined, essentially entirely automated, makes that photogrammetry becomes a viable alternative to laser scanning in certain contexts. And when I talk about heritage at the end, I'll show this. Now this is just a rough table that's trying to see like how do they compare. Data density, laser scanning just gives so much data. So in terms of LOD, probably definitely beats it still for similar applications. If you go very, very close if you want to do very close photogrammetry, then photogrammetry can definitely beat laser scanning. Accuracy, laser scanning is so much better. And what is very important is laser scanning is more robust. As I said, laser scanning works in almost any environment. You can beat it, but it's really robust. Photogrammetry is very sensitive to lighting conditions and materials and things like this. Even though they have made lots of progress, they still have some issues, so it doesn't work everywhere. Now the cool thing about photogrammetry is, like high-end SLR cameras cost, comparatively nothing. And so that's why people really look at this as an alternative. Now the key thing is that these give you only data, we always heard that, and the matter is getting the information, valuable information out of that point cloud. And another key limitation of both technologies is that they only have line of sight capabilities. So occlusions are problematic, which means that people need to move around, rescan or retake photographs, etc. And that does add up a lot on data acquisition time. So Scan-to-BIM, so it's going from nothing, scanning a building, and hopefully get a BIM model. Now that's the vision. The practice is like, a BIM. What is a BIM model? Let's say we want to have a model made of 3D individual objects, identifiable. Let's call it that's the BIM model. That's the star, So where are we at? That's another example of getting a point cloud and trying to develop some sort of at least 3D model, if not BIM model. And this is, I'll use the diagram later. So again, the idea is to go from as built or as is state, so data, and try to get into some format that is more informative. Okay, so it's going from the right to left, and that's Scan-to-BIM. But the problem, as I say, is to go from that data to the information, and a lot of the work that has to be done is you need to recognize those objects, extract them, segment the data into these different objects, and then model them. And how is this done at the moment? Obviously, there's a lot of manual work. People would select certain points in the point cloud and try to model them. But now, all the commercial solutions, some of them, I just picked a couple, but there's plenty. A little bit more semi-automated. For example, here, I point in the middle screen. I'm sorry, I don't have 3 hands and 3 pointers. But here, the user would just select a region, and actually the computer would understand more or less that this is actually a cylindrical pipe and will fit a cylinder to it, and probably extend it all the way to the flanges. So some can do with more than that. So there's still quite a lot of involvement of the human, and this requires some expertise, having experience in using this software and spend the right amount of time. So obviously a lot of people, including those companies, are spending a lot of money trying to further improve the process. Here there's also a lot of work in academia, so everybody wants to go and get a piece of market share of that huge market. So lots of colleagues are trying to come up with the next magic algorithm. So lots of research, US, so US university, this is Canada, Spain, this is Korea. All over the world, everybody is trying to develop some algorithm. This is an example from Korea, where the point cloud is essentially automatically segmented, at least in 2 kind of objects. There's these pipes that run around, and then, so it's not model, it's just putting the points in different groups, but the next step is modeling. So lots of work, but we are actually far from having the silver bullet for this. There's a lot of work to be done. You will still need a lot of experts for quite some time to do these activities. That's another, that's the example, that's from Manny, actually. I do have something from him. Again, a different kind of work here. They're trying to segment the different parts. And that's state of the art. And we are nowhere near a model that knowing this is actually a pipe, this is like a beam, slab, etc. That's state of the art. So lots of work. Now, there is in object detection and modeling, maybe I like the latest work from Carnegie Mellon, probably this, the coolest thing, and it seems ridiculous as a result almost, but they started from a point cloud of rooms, actually the entire floor, and they could segment the walls, the ceilings, and then inside those trying to detect what are the windows, where are the doors, and try to create at least a rough model. So at least here they start having a bit of structure. So they have a model. The model is made of walls, floor and ceiling. So you have the semantics that starts appearing, and then there are doors. They have the location of the door, etc. But it's approximate. It's not perfect yet. It's just progressing. So a lot of people would say too slowly, but we try best. Promise. But this is only the case, and this is very important. Scan-to-BIM almost does not predate BIM, but creating 3D models from laser scans, the context within which it developed was about, we've got nothing. Essentially, we had these 2D drawings, printed drawings, and essentially nobody trusts them because they've never been updated. So the first thing they do is they trash them and then say, okay, we want to have a clear view of what the facility looks like. And so this is where it comes from. So the idea is like, this is a blank sheet, we laser scan and we try to get a model out of this. But what is happening is obviously now a lot of people are designing in 3D and using BIM. Actually, you don't need necessarily the whole BIM thing, but at least designing in 3D. And there are plenty of applications where, especially for quality control, where you would want to use a laser scanner and know whether things have been built properly. And so there's a big growing market, if you want, where you don't start from a blank sheet. You actually have a model that comes from the designer. Now the model may not actually be exactly what has been built, but it's pretty good, usually starting point. So what we were looking at is, actually, what about trying to process those point clouds in a more efficient manner, assuming that we already have a model coming from the design team. So that's called Scan versus BIM. We already have what we call an as-designed 3D model, and we've got the as-built data, and we want to process that, segment it, and look at the data, well, extract information out of it. So it doesn't apply in all cases, but it's applying in a growing number of cases. At the heart of it is the alignment of the point cloud in the reference system, the coordinate system of the BIM model. So this is an example we run. This is actually quite old. We did that like in 2000. That particular case was in 2067, something like that. But the data has been very good for us to continue work. So the idea is, yeah, if you put it in the same coordinate system, and you can do that, you can use geo-survey points. It's not going to be exactly perfect if we have surveyors in the room, but you get some really good alignment. We've done it for structural works. And the next slide is a video that kind of shows then what happens afterwards. Okay, what can you do afterwards? Now, before I show the video, if you had that point cloud and you were to assess the slab of the first floor or the columns here, actually on the live job, there's plenty of stuff here that is just including what you want to do. There's the safety barriers, there's a crane, there's plenty of things. And if you were to process that point cloud, you'd have to go inside it and try to figure out what you want and slice it, and you try to isolate what you really need. And this is where the video will show that just by aligning and using some algorithms, we were at least able to do that, which is quite valuable on its own. So this is the BIM model and the point cloud in the same coordinate system. And at the time, using some proximity kind of approach, we could at least first say, well, which point here corresponds to an object in the BIM model and which point doesn't. Okay, so here in green already we've started segmenting out what we think is not of interest to us. So I think in a second it will, sorry, here you go. So now we have a point cloud of just the facility. So none of the things we don't necessarily care about. This said, if you had the safety barriers in the BIM model, you could actually try to get the safety barriers point cloud and check them as well. So you get the point cloud. You have, for example, a point for this wall here. And what is very important, I can't pose, but it looks like it's once we split the model into the non-BIM model and the BIM model. Actually, we've got here the sub-point cloud for each one of the columns, the sub-point cloud for each one of the slabs, the sub-point cloud. So we've really subdivided like actually hundreds of objects. And then if you want to look at this, just this elevator shaft wall, here you go, now we isolated everything and we can start doing maybe some measurements. And look, the coloring of the points here was about the distance of the point to the wall. Okay, so it gives you, a lot of people, you can do that in some software already, and it gives you at least an idea, and you can do some click, you can click on the point here and it'll give you what's the distance to the wall. So that was already valuable, and actually just the fact that you can segment the point cloud into all the different objects makes your life so much easier if you were to remodel the facility, for example. You can clear a lot of things and focus on what you need to do. But that doesn't stop here, okay? If I go again to my elevator shaft, as a construction company, I want to make sure that the wall is vertical, or as a client, I want to make sure that this has been done to standards. And so I have to apply many different standards that have been selected for, is this vertical, for example, applying inclination. Specifications are, well, flatness may not apply here, but it would apply for slab, and I'll show that later. But how it works at the moment, if you didn't have laser scanning, maybe I assume the the surveyor would come and pick some points across the shaft at the bottom, in the middle, each floor, and then compute these values and say, yes, tick, it passes. Okay, so maybe there is a bit of yellow here, but I pick these points, and when I apply this tool, well, this specification, it passes. But now, obviously, with laser scanning, you get so much more data, right? I mean, you can do that. In the old methods, there is a potential that you got lucky with the points you picked, right? I mean, you could have moved your toll station by like a meter on the right, and all of a sudden you fail. And actually, the contractor may have done it his way, and then say, well, it passes. And then the client comes to the surveyor and comes and actually, no, you failed. It's like, no, I passed. I did it. I passed. No, you failed. Look. And then you go again, and then, it's not too sure. Maybe you're lucky, maybe you're unlucky. Here, at least, you could actually use a lot more data, and you could approach it in a different way. If I take another example, if I take, for example, I'm pointing in the back so the people won't see me. I'll try not to point the eyes, but if I take the corner point there in that room, okay, so people might come with a laser toll station and point that corner and try to get that corner point and say, well, this is where the room corner is, okay? And this is, because of the technology we had, like toll stations, this is what we're doing. We were doing point-based surveys because this is what the technology. But now, we got laser scanners. And these scanners, we need to shift our view from a point-based approach to a surface-based approach. So if I were to scan this room, the corner there would not be a point. It would be the intersection of 3 planes. And that's the real corner point. Because if I try to get the toll station, I might just miss a little bit. You don't know exactly, you don't really get the true corner point. But with a laser scanner, this is what the real corner is. It's the intersection of 3 planes. And this is what here, same idea, the idea we need to move away from this point thinking, point approach to survey to a more surface approach survey. And the next slide, I will show some of the works we've done to demonstrate that it can be a lot better. So my focus now, I'm moving to floor flatness because this is a great example of moving away from point-based survey to surface-based survey. How do people do floor flatness control right now? You have a range of methods that have evolved over decades, but started with the straight edge, and I'm sure it's still probably widely used. Well, you have like I think it's 2 meters in Europe, but it might be 3 yards in the US. And you put the straight edge on the floor, and you come and you measure if there is a caving of the floor, and you measure the maximum, and then you do that a little bit everywhere in the slab, and then you calculate the average, and if you pass the threshold, you're okay. Now, it totally depends where you put the straight edge, and you cannot imagine that somebody could put in this room only. I mean, how many locations would you actually have to measure to have a good idea whether the slab is flat? So for a room like this, it might not be super critical, but if you go to a warehouse where you have rolling vehicles that need to be very stable and cannot suffer from starting vibrating, forklifts, then flatness needs to be a lot more stringent. And so people start developing different measurement methods or specifications. One is called the F numbers, and recently, okay, I must not. Then there is another method I'll talk about later. And what is it based on? There are different tools that exist, but this is one of the tools. And the idea is that, should have put a video because it's really nice to see, but people draw a line across or series of lines across the slab, and they make a measurement like every foot. So this thing flipped from this leg to that leg. And they look at the profile along that line, okay? And they do that across the whole slab, and then they they apply some formula. It's actually one of the curious things about that method is it's really black box formula. It's really hard to understand what's happening with the data, but somehow it's spitting out a number, and hopefully you pass or you don't pass. So again, this is moving, it's much better, but yeah, you're still looking at like one line. It's one line, I think they said you have to do it like every, at least every, I don't know, few feet or something like that. So it's a very coarse measurement. I mean, if you're lucky where you put your line, you will totally miss a cave in the slab. So what we plan to do first is demonstrate how laser scanning could be a technology used as an alternative to capture data of floor slabs and then calculate flatness. To demonstrate that the technology itself provided the right data, we said, okay, we apply our Scan-vs-BIM, so we went out, we scanned a room, 2 scans of a room put together. We had a BIM model of that room. Using the alignment I showed later, automatically the system finds which points come from the slab, and then we had an algorithm that automatically applied the straight edge. So you can think of it as virtually coming with a straight edge and put it anywhere on that slab and looking at the deviations. But we also have done the F numbers method, and actually the other one, which is probably the state-of-the-art approach, is called the waviness index method. And well, I'll talk about the CWT afterwards, which is our contribution. But we want to say, well, does the laser scanning data give me at least the same results as you would have obtained using the same these existing methods? So using the straight edge in particular, what we did is like we created this grid. So each one of those edges here is like a straight edge. So we created a square grid of straight edges. We went in the lab, we measured manually, and then we take the laser scan and apply. This is done totally automatically. And what we found is actually we got essentially the same results. And in fact, the straight edge for which the deviation was the maximum was found to be the same one manually and using the data. So a lot of people have been saying, well, the accuracy of the data, blah, blah, is not, maybe it's not enough for these kind of applications. We don't see that. We don't think that's true, actually. And then we say, well, obviously doing 10 strategies actually took some time in the lab, but the cool thing is the computer then, you could generate plenty of strategies wherever you want randomly. That takes a fraction of a second for a computer. Or you can generate more, maybe smarter patterns, how you should apply the strategy. So you can actually do better than current methods. And when we created those much denser patterns of strategies, we found actually that the true deviation was the maximum deviation for the random and what we call the grid star pattern was actually higher. So what we meant to show here is that, yeah, this person did these 10 ones, they just got lucky, because the maximum deviation happened somewhere in the middle of that square, and it just happened that the strategy was not there. So at least using the computer, the TLS, the laser scanning data, and our method, we could generate tons of strategies and show what is probably much closer to the true maximum deviation on that slide. Is that all right? So move on. So what we did then is we also applied the waviness index methods. So waviness index is similar to the F numbers, using similar measurements, and is looking at, I think it's 5 different wavelengths. So it's looking in the profiles, so linear profiles on the slab, and it's looking for certain wavelengths, because these are the wavelengths that the forklift will start coming into vibration, and therefore there is a risk for the operator and everything. So they are very keen to know, is there any such wavelength in the profile of the slab? Lower wavelengths, no problem, you won't feel it in the forklift. Higher, same thing, they won't feel it. But there is a range within which there is a risk. And it's related, by the way, to the spacing between the 2 axles of the forklift. So the wavelengths that you have to study. So normally you have to do these lines on the slab. We've done them much longer. You can see the profile data here expanded. And you can see again the profile data, and they calculate at 60 centimeter wavelengths, 120, 180 to 300. And they get some number, which I like because contrary to the F numbers, you can actually figure out where it comes from. It makes a lot more sense to the mind, so that's a good thing about that method. But we said, okay, we can get good results with this, but it's the state of the art, but it's only like linear. It's still about drawing lines and picking measurements here and there, while really surface flatness is a matter of surface. It's not a matter of lines. Okay, so you should look at other things. The other problem of this one is that it only measures at 60, 120, 180, 240, 300, but doesn't give you in between. It just kind of samples the points and try to get an idea. The first thing we did is we applied something called the continuous wavelet transform. It's been recently published. And the idea here is that we can actually, using the same data as they use for that method, and using this algorithm, I don't want to go in detail, but we could get the location of peaks or waves in the profile very accurately, both in spatially but also in the wavelengths domain. So instead of having a point here, these are the wavelength periods, instead of having a point at 60, 120, 180, etc., we got lots of granularity, and you can figure out exactly where it's picking. So here I'm pointing at the red area that picks probably somewhere, I think it's from somewhere to the top. And what it's telling you here is that at a wavelengths of 400 centimeters, at the distance 400 centimeters down that line, there is a peak. And indeed, if you look at it at 400 centimeters down that line, we have these big wavelengths. Okay, so it actually finds this, but with much more granularity than the previous method. And when we looked at the correlation between the two, we found that the continuous wavelet transform was giving really good correlation with the waviness index. And actually, we found that the waviness index is actually quite weak on the 60 centimeter wavelengths because it doesn't use enough data. It just takes a point every foot and actually gets confused and misses things. So we actually found we could, well, it seems that it's actually outperforming it. I mean, to my mind, it should outperform it. But we were trying to demonstrate that it does outperform. So what I was telling us is wavelet transform, now we can get if I go back to the straight edge you look at 2 meters. This is one wavelength, essentially. They're just looking at, put the straight edge, 2 meter, and they look at the spacing below. That's one wavelength. Then the F number is trying to look at more kind of wavelengths. The waviness index was doing 5, and now we can get with this essentially the whole granularity as much as you want. Okay, so we have improved in that direction, but the problem is still done on lines. Okay, and as I said earlier, we want to do surfaces. But the cool thing is that that method, the continuous wavelet transform, works in 2 dimensions. So you don't actually need to do along lines, you can do it on 2 surfaces. So if I take my slab here, this is what the surface profile looks like. Okay, so the yellow are points that are kind of going above the flatness of the slab, and the blue, they are going below. So we used to draw lines across this and hopefully come across these points, but we didn't see that point. But now with the 2D wavelet transform, we can actually process that data and identify here that there seems to be a 300 centimeter bump, if you want, 300 centimeter wavelengths bump in the data. And we can give you the whole wavelengths profile. Essentially, this is not what you want to show. You want to have this in the background if you really want to see where the problem is, but you can compute that data and actually have much more accurate view of what is the flatness profile of that slab. And then if you show that thing, this is the information you could send to the construction crew and say, well, you need to flatten that area, okay, because it's actually too bumpy. So you could give the map of the slab on the BIM model. You can actually map this on the BIM model object, so then they arrive, they can see the room, and they say, oh yeah, that's where I gotta go, and make it flatter. So it's a lot of maybe math for things, but really the idea is to say, we can, a lot of the construction quality control methods we have at the moment are based on these point-based measurements, which is totally outdated compared to what laser scanning can give us. And this is just one example where we're showing, well, the density of data, the accuracy of data can be very, very powerful, and we can deliver more accurate results, but we can also maybe rethink the way things like flatness control should be assessed nowadays. One last slide on the matter about scan versus BIM and this quality control. And it's just not just about laser scanning, but there is obviously a link with building information modeling. So I believe most of you will be familiar with the National BIM Library, NBS Create. I see knocking heads, that's great. So obviously now, if you have a BIM authoring platform like Revit, you can drag and drop objects from the National BIM Library, and those objects will have actually linked specification, standard specification documents that you can map to them. So you drop the object, and actually it will keep the link with those specifications. Alternatively, you can actually create your own object and then link it to a set of specifications in NBS Create. But the key thing here is that we have a BIM model, we have the specifications. So if you think about floor, slab flatness, we'll have the slab, we have mapped waviness index, methods, and we want a super flat or whatever methods they use. And this is all digitally available. So the algorithm we have here could read that data in the BIM model and directly apply the algorithm and then report the results. So all things are coming together. And actually, just to please Bill, you could, I don't know, if you need that data, you could export it afterwards in Kobe, only if you need it. And so that was just a wrap on this Scan versus BIM. It's been going on for a while. We've tried to push at the beginning because there was not that much BIM going on, and laser scanning was still not that common. People didn't have much interest, but obviously now there's a lot greater interest. And I actually think there is a company in the US that is now selling a Scan versus BIM solution, which they didn't ask for the term. I'm glad they used the term because we came up with that. So later on, I'm happy to get any question on this. The second thing, and it's a bit shorter, I want to talk about is heritage survey. This is a project we've just completed with Historic Scotland. Actually, we will most likely continue the project further soon. What we did, we went to Craigmillar Castle in Edinburgh. If you've never seen it, it's nice. One of those nice rooms that you find all over Scotland. And we wanted to first compare various survey technologies, and in particular photogrammetry and laser scanning. Some people have done this before, and we went back at it. Another thing we looked at is how can we use the point, how could we demonstrate how you could use the point cloud in a meaningful way for various people. So the first thing we did, we went out with, on the same day, we had 2 scanners. We had a photogrammetric system. I'm sorry, it's a bit dark photo, but this is a SLR camera on a 5-meter pole. So they didn't have it all the time. They had it first at ground level, and then they raised, and then they raised, and then they raised. Took a log picture of about 10-meter high wall castle rampart. We had a drone with equipped with a DSLR camera as well. And finally, we had a stereo camera system, which I personally believe in, but the one we had for that experiment ended up being bad quality. So the results on that are really good. So we need to go back and get a better system, or probably build our system and compare it. So the main idea is that, well, laser scanning is great, but can we achieve similar result with photogrammetry, which is a lot cheaper, and actually with UAVs? Because in a lot of heritage contexts, if you want to survey a building, if you take a survey cathedral, the laser scanner, very quickly you get these huge incidence angles, and you get stones, occluding the next stone, so you can't see mortars, for example. You'd like to know if the mortar is coming off. You can get that. With the drones, the cool thing is you can always get the best view almost, but the problem is, does it give you good enough data? Does it compete with laser scanning and data? So we had this is the point cloud generated from one of the laser scanners. This is one we had on the pole-mounted system, and this is one we had from the UAV. And you can see here it zooms on sections, a little part of that castle. The first thing you can see is that the density of points for the photogrammetric, so the last two rows, is actually not bad at all. It doesn't quite compete with the laser scanner, but it was really good, very good result. And the second thing you cannot see here is that actually the pole-mounted photogrammetric system did almost as well, very close, than some of the laser scanners, one of the laser scanners, which many people would not necessarily think is the case. To get those, by the way, we took pictures about 5 meters from the wall. And same here with the UAVs, we were about 5 meters from the wall. Now the UAV, however, that's a problem with pretty pictures. It looks really pretty, but actually the data was not very good quality. And again, this is something the surveying company learned on the job. They made a mistake. They thought they actually, at the end of the job, they were much longer than all the others, and they came out, wow, we did a really good, thorough job. I think we'll have good results. And actually, what happened, they took like a bad focal length, and actually that had an impact they didn't expect would have. But I believe that it could get very close results to what you get from, let's say, more stable, pole-mounted or hand taken camera. So we didn't discard at all the drone for future consideration, but unfortunately on that experiment, the surveyors didn't do really the good job we thought they had done. And when we saw the result first, we were like, oh, that looks great. But actually, when you compared with the scanner, there were some parts that were very few points. There are some parts where the reconstruction is not very good. So that was one of the things. The other thing I wanted to do is demonstrate how you could use the data. These castles, they need to be renovated, obviously every so often, and you need to define when are you going to intervene and what you are going to do. And if you take like these kind of rubble stone walls like this, one of the things that would need to be assessed is how much there is mortar recess along that wall, and where should we repoint the wall, or maybe should we need also to add some pinning stones here and there. That's one of the things we're looking at. Or maybe as a stone move, because this is a consequence of recesses that maybe some of the stones moved. Yesterday, Stephen Fife talked in Canada an example of where stones were moving. So one of the things you would want to do here is isolate the stones from the mortar, but that's not an easy thing to do. But we did work on an algorithm that kind of does that. Okay, so the idea is like if we can tell where there is a stone, then we know where there is mortar, and then we can, for example, analyze the mortar. Or we can say, well, this is a stone, and from the scan 5 years ago, we can match the stone and see, well, actually that stone has moved outwards a little bit. In Scotland, every year there are accidents because of old tenement buildings where stones are coming out and not fixed on time. And this is, for example, where it could be applied. But if you want to bid for jobs for doing this kind of repairs in the UK, now I'm not an expert in this, but I know that a lot of this, the way it's done is by meter square. So essentially, they calculate the square meter of wall, and they apply some rule of thumb that tells them this is how much work you have to do. So here we'll say, well, actually, since we know where the stones are, we can calculate how many meters of mortar there is in the stone. And we found, in this case, for example, we were finding there's 110 meter of mortar on that wall, when the truth, when we looked manually, was about 125. Okay, so it's not perfect, but it's actually much better than current estimations, which are just based on very random rules of thumb. Well, not random, but very approximate rules of thumb. But then once we have the center line also of those mortar regions, we could look at the depth of them, so figure out if there is some recess where it is located, and point the surveyor to these regions. And also here I think we have the width of the mortar regions. And finally, just for it was more for the fun of it than anything, but we were trying to say, well, if you were to repoint that area, where would you put pinning stones? And if you know where the stones are, you can figure out which zones may require some pinning. And this would be would give an estimation, well, this is how much pinning you need to do on the job. At the moment, these things are calculated very, very, very approximately. So the data can be useful, not just for the person, for the tourists to create pretty pictures, or for other management authorities, but even down to the person who's going to price works, repair works, that can be very useful. Keep in mind that this section is 8 meters up the wall. Normally they would have had to build scaffold. It's like, some of these things, you can't even tie the scaffold to the wall because that would damage the wall. You need to build some complex scaffolding solutions. Like, you can save a lot of costs. And by the way, the method works not only on flat walls, because a lot of methods you see seem to work only on flat walls, but this actually works on, this is the tower section, and it worked really well on the tower section as well. It's not perfect, but it's better than what we have right now. So, generally, conclusions, significant efforts in Scan-to-BIM, and it's not, we are far from being finished there. And then growing interest in Scan-vs-BIM. I truly believe that there will be tons of applications, especially for quality control of works. Or if you come back down the road during FM, you could rescan your facility and see sagging in pipes and other things. This could, Scan-vs-BIM would be very helpful there. Well, not adopted, as I said, now, since I wrote, I figured there is a company, I don't know if they have done any particular work, but they're trying to sell such a solution. And I think it's very important. Like, the laser scanning in general has, I think, leading to some paradigm shift, leading to surface-based controls. Now, actually, I'll show you a slide after. This doesn't work all the time because the method we used at that stage was about using proximity of the points to the objects. But if you take this is a laser scan aligned to a BIM facility, well, BIM model, and sometimes the point cloud is really clear which object they belong to. Sometimes we can work with that, it would probably work, but sometimes actually the current method wouldn't detect that really well. So we need to think about these further and create new algorithms. Due to time constraints, I'll skip that. And yeah, so, laser scanning BIM, we've only scratched the surface. And one of the key messages I wanted to give at the end is that you shouldn't think about the value of BIM just for the sake of BIM. As you can see here, by leveraging the as-designed BIM model, we can actually improve a lot of things during construction, such as quality control. And again, also laser scanning can make BIM a lot more valuable. So they all benefit from one another, and the decisions to go for one, the decision to invest in this technology should not be made in silos and should be thought of more globally. Thank you very much. Sorry for the extra time I took. I just want to point out one thing. I'm on the board of IARC, and not many people know about this. Alan, do you know ISARC? You probably do know ISARC. And we run an annual conference. It's about automation, robotics, construction. And I do love the works I cited. A lot of people publish there. You can attend, everybody's welcome to attend, even present. The cool thing is that all our proceedings are free online on the ISARC website. So if you have an interest in all those things, at least you can get those for free. So it's not the journals, but it's at least the conference paper. So then the bottom one is the Automation Construction Journal, and that's what I'm an editor of. And that could be, some of the papers could definitely be published in a special issue, yeah. Anyways, thank you very much.